and good morning, everyone, to the Association of State Floodplain Managers Annual Conference. This is section G6 on stormwater permitting, planning, and projects. I want to thank the attendees to the conference. I want to thank our sponsor, Tetra Tech. Tetra Tech is our sponsor for this particular session. You can go on the website and click on, when you go to the exhibit hall, and click on Tetra Tech's button, and then you can go into their exhibit hall area and so get to see the services that Tetra Tech provides. I want to encourage everyone to, as you're listening to this, to insert your questions into the chat panel on the right. We will be using the questions from the chat panel after each of the speakers. Our first set of speakers, and the full bios, I'm not giving you bios, the full bios are below in the page you're looking at. You can go look at them. But the first presentation will have three speakers, and that's Dacia Mosso, Sam Sarkar, and Caitlin Van Hagen. The title of their talk is Using Planning and Nature-Based Solutions to Achieve Co-Benefits for Water Quality and Hazard Mitigation. So now, Chuck, if you cue up that presentation, we'll watch the opening speaks.
Hi, my name is Dacia Mosso. I'll be kicking off our presentation and will later be joined by co-presenters Sam Sarkar and Caitlin Van Hagen, also from Tetra Tech. Caitlin and I are environmental scientists who work on a variety of projects involving planning, outreach, and protecting water resources. Sam is an environmental engineer who supports projects involving planning, stormwater management, EMPs, and flood mitigation and resiliency. Today we'll be talking about using planning and nature-based solutions to achieve co-benefits for water quality and hazard mitigation. As I'm sure you've seen in the news, natural hazards are growing in frequency and intensity. Just as natural hazards don't abide by jurisdictional boundaries, management challenges and impacts of natural hazards don't remain within agency and program boundaries. Opportunities exist to better achieve mitigation and environmental goals by using environmental protection as a mitigation goal. Hazard mitigation plans are required for a state to be eligible for certain FEMA funds. So these plans are a logical place to highlight this connection and plan appropriate actions. Several states have successfully integrated environmental goals into mitigation plans. We'll provide HMP excerpts from these states later in the presentation. Alone, natural hazard and water quality programs face barriers to success because they have limited resources and staff to tackle issues. When programs are integrated, success of achieving mitigation and environmental goals dramatically increases. This makes sense because the issues aren't independent, nor should they be siloed. Natural hazards affect water quality. For example, heavy precipitation events and rain on snow events often lead to flash flooding in vulnerable areas. Land management and planning can exacerbate flooding by changing the perviousness of a watershed and leave communities more susceptible to inundation. Uncontrolled discharge of pollutants, so for example chemicals, during flooding can also pose risks to groundwater and surface water. Water quality impacts health risks. For example, harmful algal blooms can pose a threat to human health and aquatic communities. Toxins produced by certain harmful algae and cyanobacteria can cause water-related illnesses in humans, pets, and agricultural livestock. Exposure occurs through direct contact with recreational water or consumption of contaminated drinking water, fish, and shellfish. So the goals of today's presentation are to see how nature-based solutions can be used to protect water quality and help mitigate natural hazards, review a local project using nature-based solutions, learn more about major water quality planning and funding programs. Note that we won't go into detail about hazard mitigation planning since we know this audience is familiar with the HMP planning process. We'll walk through efficiencies gained when integrating water quality and hazard mitigation planning, and we'll learn how to set goals and strategies that allow for integrating the two types of planning. For those who are unfamiliar with the term nature-based solution, basically we mean green infrastructure type practices. Nature-based solutions can be used to protect water quality and reduce natural hazards. There are numerous practices that can be used to achieve your goals. We'll go over some examples in the next slide. What's great about these nature-based solutions is that one practice can address multiple hazards, which increases efficiency and saves time and resources. Practices can be urban, such as including parks and areas to trap stormwater, rural, such as creating meander buffers, or agricultural, such as cover crops. This is a graphic we developed to show example nature-based BMPs with co-benefits for water quality and hazard mitigation. The graphic illustrates the different natural hazards a practice can address, as well as level of overlap of the mitigation benefits. So for example, in the first row, regional infiltration basins can address flood, fire, landslides, drought, and airborne dust particles. And of these, there is strong overlap for flood, landslides, and drought, and there's only partial overlap for fire and airborne dust particles. Now that we've reviewed nature-based solutions at a high level, let's move on to a local example of this. And for that, I turn over the presentation to Sam Sarkar to discuss the Dallas Water Gardens, planned south of downtown Dallas. This project aspires to combine the city's enthusiasm for public green spaces with flood hazard mitigation and water quality improvement.
Thank you, Dacia. The Dallas Water Gardens is a project planned south of downtown Dallas in the Cedar neighborhood. The Water Gardens combines the flood control objective of the Able Sump Station with the city's enthusiasm for public green spaces. This project aspires to convert 6 of the 9 ponds in the Able system to constructed wetlands. This wetland buffer between Dallas and the Trinity River will benefit both the community and the environment by improving water quality, entering the Trinity River by filtering pollutants, reducing flooding by storing excess water, creating recreational opportunities by adding boardwalks and green spaces. The actions that ensure long-term success of the Cedar neighborhood project include incorporating future community investments and goals, monitoring water levels to document success and indicate maintenance needs, integrating other area projects, including the Dallas Floodway Project, the Trinity River Corridor Balanced Vision Plan, and the Dallas High-Speed Rail. The initial system design of the water gardens generally consisted of field activities, hydrologic and hydraulic schematic design, and ecological design. This initial study, completed in June of 2019, included an inventory of ongoing and proposed infrastructure projects in the study area, evaluation of soil properties, groundwater and surface water quality evaluations, hydraulics and hydrology modeling, water quality modeling, and concept schematic and ecological designs. The analysis consisted of evaluating several alternatives for mitigation of increased flood risk due to the conversion of the upper ponds to constructed wetlands. The evaluated mitigation options included capacity increase of the upper ponds via lateral expansion and excavation, using a gated structure to release water before a major storm, and adding underground storage features. Each option was evaluated against 8 guiding principles and consisted of evaluating flood risk, water quality impacts, impacts to the local economy, habitat creation, connection to the Trinity River, visual appeal, mitigation of urban environmental impacts, and opportunities for active recreation and wellness. The recommended alternative consisted of a weir between ponds 3 and 4 as the primary water impoundment structure, and increasing the capacities of ponds 5, 7, and 8 through a combination of lateral expansion and excavation for flood risk mitigation. The assessment of hydraulics and hydrology of the existing and proposed conditions were completed using XP-SWIM, a commercial version of the EPA stormwater management model. Important considerations for the modeling were the Able Sump Station and sump connectivity, existing and future pond connections, Able Sump pond interaction and sensitivity, and the 100-year floodplain. All proposed alternatives were designed so as to not to exceed the 100-year floodplain criteria. The stormwater model was also used to evaluate long-term hydrology conditions and to assess water quality impacts under existing and proposed conditions. The long-term modeling was also used to establish different zones associated with the constructed wetland and discussed later. 4 alternatives were evaluated. Option 1 consisted of widening ponds 4 and 5. Besides a weir, this option requires expanding existing pond footprints onto nearby vacant parcels. Option 2 consisted of deepening pond 4, which requires excavation of 2 to 3 feet below existing pond footprint. This is not an ideal option since the normal pool depth is shallower than desired, and there's potential for more pollutants entering the upper ponds during smaller events. Option 3 consists of an automated control structure, which would require the city to operate the automated slide gate to reduce normal pool prior to large storm events. This option also does not require excavation or pond expansion. And option 4 consists of underground storage. This option also does not require excavation in the ponds and instead proposes using underground storage or infiltration basins to temporarily store water. All the above 4 alternatives were evaluated against 8 guiding principles, which consisted generally of connection to the Trinity River, mitigation of urban environmental impacts, enhanced visual interest, improve water quality, absorb storm events, encourage active recreation and wellness, create habitat, and boost local economy. Stormwater wetlands are comprised of continuous vertical zones that mimic the structure and function of natural wetlands. Zones are defined by relationship to permanent water level, frequency of inundation, water depth, and/or slope. Different zones provide different ecological services, including but not limited to pollutant removal, habitat provision, and erosion control. Wetland design, including the upper bank, temporary inundation zone, transition zone, and deep pond, were informed by the hydraulics, hydrology, and water quality modeling. Plant community selection for each wetland zone was based on suitability for the given geography and climate. The subsequent phases of this project will consist of design and construction of Katie's street and riverfront bridges, subsurface utility engineering for adjacent utilities, survey of upper ponds, forebay or green infrastructure to prevent pond sedimentation, and U.S. Army Corps of Engineers permitting. With that, I turn it over to you, Dacia.
Thanks, Sam. So the next part of the presentation, you'll learn more about water quality protection and planning at a high level. So what are these types of planning programs and what do they achieve? You'll understand efficiencies gained when you integrate water quality and hazard mitigation planning, and then you'll learn how to accomplish all of this. All right, now let's dive into an overview of water quality programs and associated plans, the program objectives, and elements of each program that are relevant to hazard mitigation. EPA water quality programs include the MPDS program, which regulates point sources like wastewater treatment plants, industrial treatment facilities, and stormwater from construction sites, urban separate storm sewers, and industrial site runoff. As many of you know, the stormwater permitting program for cities with MS4s has been actively supporting the kinds of joint flood control and mitigation and water quality objectives that are at the heart of integrated hazard mitigation and water quality planning. The non-point source pollution control program overlaps significantly with hazard mitigation goals. The MPS program, which includes a planning element using watershed plans and cost share funding to implement BMPs, is particularly relevant for hazards that might be related to drainage management in more rural areas. Next is drinking water source water protection, which protects sources of drinking water from harmful pollutants, such as chemicals, sewage, and other harmful substances. Another relevant program focuses on wetland protection and restoration. Wetlands, healthy soils, and surface drainage networks stabilized by natural vegetation comprise a significant portion of the green infrastructure we've embraced for achieving water quality and water quantity objectives. Wetlands have incredible clean water and flood mitigation benefits. Finally, the Water Quality Standards Program ties everything together. Standards include the designation of beneficial water body uses, such as recreation, drinking water, and so on, the development of criteria that protect those uses, and anti-degradation policy and implementation methods to prevent lowering of water quality except under certain conditions. Note that throughout our presentation, when we talk about watershed planning, we're talking about plans that can encompass elements from all of these water quality programs. All of these water quality programs have elements relevant to hazard mitigation, but in the interest of time, I'm just going to focus on two. Stormwater management plans developed as part of the NPDES program are included in the HMP checklist of requirements. The NPDES program also implements activities that alleviate flooding hazards while improving water quality. The key elements of the watershed-based planning approach used by the NPS program include point source and non-point sources of pollution, through a process that closely resembles the planning steps for hazard mitigation planning and the National Flood Insurance Program's Community Rating System, or CRS, program. BMPs funded by this program can also reduce hazards. For greatest effectiveness, it's a good idea to base NPS watershed plans on the flood and drought risk components of HMPs. I've mentioned hazard mitigation planning without going into detail. As many of you know, hazard mitigation planning involves engaging stakeholders, conducting an assessment, defining goals, identifying opportunities, and creating a strategy to address problems or deficiencies. You can readily see that these basic steps closely parallel the steps for developing a watershed-based plan shown here. Knowing that hazard mitigation and watershed planning encompass very similar planning processes, incorporate many of the same mapping, engineering, and technical considerations, and target almost identical aquatic, terrestrial, and infrastructure assets makes the leap from silo-based programmatic planning to integrated planning that much easier. Now that you have a better understanding of water quality programs and planning, let's look at how to integrate those planning steps with hazard mitigation planning. I'll do a bit of a crosswalk on the planning programs and their steps, discuss which stakeholders to involve, and talk about funding opportunities. In this diagram, CRS steps are shown across the middle in the brightly colored arrows. Hazard mitigation planning steps are shown across the top, and the watershed planning steps appear across the bottom. Both types of hazard mitigation planning steps are included in this diagram to accommodate users who prefer to follow one set of steps over the other. The connecting lines show how the HMP steps relate to the CRS steps. The numbers indicate where the watershed planning steps overlap. Please refer back to the recording of this presentation if you want to look at the details of this graphic more closely. Okay, now let's look deeper. Here's a detailed table showing how local hazard mitigation planning steps overlap with more detailed watershed planning steps. You can also do a similar crosswalk with the CRS steps. You can see that the overlapping activities begin early in the planning processes with stakeholder engagement and increase quite a bit as assessment activities get underway. This diagram shows the basic elements of who to involve and for which programs. Note that the integration of hazard mitigation and water quality program planning can and should occur at the state and local levels. At the state level, senior program managers need to be aware of co-benefits, implementation opportunities, and funding enhancements associated with an integrated approach. They can then help local hazard and water quality planners explore how best to fold their efforts together in those areas where it makes the most sense. We know funding dictates a lot of what programs are able to accomplish. By integrating program efforts to achieve shared benefits, managers can make limited dollars go further. Funding an integrated effort usually depends on the type of financing typically available to hazard mitigation and water quality planning. So grants, loans, taxes. Most people are familiar with these, and sources are available on both the hazard mitigation and water quality side of the house. This table illustrates how a locality might identify and track available funding for specific project goals or objectives. Note the additional resources shown on the left. If you don't know where to start looking for funds, those 4 bullets are a good place to start. For the last part of the presentation, I'll turn it over to my coworker, Caitlin Von Hagen.
Thanks, Dacia. So in giving an overview of planning integration, I first want to mention a few basic framework that includes some pointers taken from existing integration efforts. So following the bullets on the slide, a basic framework for integration often starts with informal conversations between people involved in both water quality and hazard mitigation to see what's already out there. And doing so will help to identify possible integration opportunities and really get the ball rolling. Then conduct an initial assessment to define key issues and identify which stakeholders are affected. Also consider making use of a third-party facilitator to keep the process running smoothly. Identify a champion and a core group of people who care about the project. This will ensure that the progress will be made. You should also understand planning specific to the community that you work in and know any specific requirements for funding or project management. And finally, it's a good idea to periodically check that you remain focused on integrating and aligning the planning effort. So early in the response to the Hazard Mitigation Act, HMPs didn't typically include nature-based solutions. And that was mostly because these weren't activities that FEMA typically funded. However, as FEMA programs and initiatives have evolved, the value of nature-based activities has been increasingly recognized. And these activities are now eligible and being funded by FEMA HMA programs. But keeping that in mind, integrated plans also need to have the vision to look beyond FEMA programs. And as the slide shows, you can add goals and strategies to an HMP that include nature-based solutions. A good time to do this is during your regular HMP update. Once you get your hazard mitigation staff, water resource staff, and stakeholders together, you can start to identify key concerns and explore where things overlap. This will inform the specific goals and strategies to include in your HMP. The process includes identifying hazard mitigation and water quality concerns, characterizing overlapping issues and concerns, and exploring integrated strategies and complementary funding support. This slide provides an example language from HMPs that already incorporate nature-based goals and strategies. The key to bringing nature-based solutions into the fold of hazard mitigation planning is to identify multi-objective actions and strategies. Keep in mind that these can include both policy-based and project-based actions. So for example, they can extend beyond brick and mortar projects to include even regulation changes. In setting goals and strategies, remember that the primary focus of HMPs is to reduce risk both now and in the future. To fully understand all risks, it's helpful to clearly define vulnerabilities, including those to the natural environment. Doing so can help identify nature-based alternatives. As stakeholders identify overlapping goals, objectives, and strategies, possible approaches for a common planning effort will likely begin to emerge. As you initiate this effort, remember to be consistent with the requirements of your funding sources. This will likely mean that the integrated plan will include specific elements supported by a range of different funding sources. It's important to keep account of activities and expenditures of each of those elements. That will allow funding organizations to see exactly where their dollars or any other support is going and how it fits into the overall plan. So this slide shows a template that the state of Washington used to plan and develop implementation activities related to reducing flood damage and also promoting ecosystem recovery in floodplains. A link to this example is included in our handout, so you can also refer to it later. We recommend that you consider using a similar template in your own tracking. You can also add additional detail and tailor it to better fit your needs. But the main takeaway is this: think carefully about who you need to involve, what you need to do, and which items you need to track. Setting up a good comprehensive system ahead of time and maintaining it over the life of your joint efforts will pay off later. For example, when it comes time to report on what you've been doing. Also listed on this slide are a few states that already integrate planning to some degree. And links to these plans are also included in the handout that I mentioned earlier. Partnership pointers. If you haven't formed a partnership yet, review your jurisdiction's HMP and watershed plans to see who provides input there. If there are gaps, identify new stakeholders. Those new stakeholders might include NGOs or governmental offices that weren't included before but could be relevant now. And then finally, contact those key players. Since that was a lot of information to digest, we think it's helpful to look at some short-term next steps. So starting with us at Tetra Tech, we are beginning to help states and counties incorporate the concepts discussed in this presentation into their HMPs. Our team has a combined knowledge of both hazard mitigation and watershed planning that has been really helpful to identify areas for integration. And also, as we work with local and state entities, we look for ways to integrate these concepts into watershed planning. We truly see integrated planning as the way of the future, especially as leveraging of limited funding becomes more and more important. And lastly, what are next steps for those in the world of hazard mitigation? This slide shows some suggestions for those who are interested. If you're updating your HMP, include water resource planners on your team so you don't miss opportunities to leverage or even join their projects. Review your state and local plans for partners, gaps, and opportunities. When writing your plan, keep in mind which hazard mitigation elements could benefit water quality, and then share that information with your water quality partners. Also, we recommend using example HMPs that already accomplish integration as a reference. And to that point, there are two examples of plans that you can reference on this slide. And then there are actually a few more examples on the resource handout that should be available for download with this presentation. And now we have a few minutes for questions. Dacia will be answering questions during this Q&A period, but if additional questions arise, please don't hesitate to email us after the presentation.
Thank you, Dacia, and the crew from Tetra Tech for that nice presentation. This issue of combining water quality and quantity impacts has been a problem in the United States for decades, mostly because those two programs, one for water quality and the other to try and reduce or deal with floods, on the quantity side, has always been a problem. They're stovepipes. They come from different agencies. They go through different state agencies, and when they get at the local level is when you're having to combine and figure out how to work these together. And a lot of communities don't do that well. It's good to see communities working on this. My first question, Dacia, would be, are you finding communities open to try to combine these elements of quality and quantity as you work along with other communities?
I would say definitely. We're actually working on a project now with a client in the Midwest who's putting on a workshop. They're bringing people together for a discussion as they plan to update their HMP. So they're looking as a goal to go ahead and incorporate a lot of these concepts and increase efficiency of funding and using these more progressive concepts of planning.
A similar question out of the chat panel is, if you've worked with specific communities, is it possible that you could name those communities so that we can find out and share that plan so that we've got a kind of a cookbook to work with? You've got a plan right here in the one you discussed. Have you got others that you can share plans on?
Yeah, so we've got a resources guide that should be available with this presentation. If people are unable to find it, go ahead and send me an email and I'm happy to get you a copy. But a couple of things come to mind, I guess, are two main sources of information related to that. There are a lot of states that are already doing this with their HMPs. So states that come to mind are Massachusetts and Maryland, Washington State, Oregon, Colorado. There's probably more than that. Local, there's the city of Portland, Oregon, and in California, since they've got that state statute that mandates all local plans developed after January 1st, 2017, they have to include future conditions and looking at adaptive capacity to deal with climate change. A key element of that is nature-based plans. And another resource I'd point you guys towards is EPA had put together a webinar on successful pilot projects that are doing this. And in that webinar, they list out, so there's 4 communities that are doing this, and they provide some information about lessons learned. So basically, the webinar link is in our handout, but the webinar will synthesize some advice and reflections of the EPA staff and consultants who are working on it, along with some of the general planning best practices that they found. So those 4 communities are Albany, New York, Ashland, Oregon, Huntington, West Virginia, and the Commonwealth of Massachusetts. So again, that link is in our handout. It's a webinar. You can find out more information about those communities. But I would definitely have you guys look at the HMPs that I suggested. And some of those are sprinkled throughout the presentation that we gave.
Yes, and people will be able to go back and pull up the presentation too. The other thing I would ask you to do, Dacia, is we won't probably get to all the questions today. So if you can go back into the chat panel and answer those questions, I think people, when they go back and pull up this presentation later on, will be able to see the chat panel and the questions that were asked and the responses you provide. So that would be helpful if you would do that too.
Okay, yeah.
So one other question I wanted to ask you is how much land will be needed for this particular project, needed to purchase?
So I assume the question is related to the Dallas Water Gardens project, about 80,000 square feet for the recommended alternative. And I'm pretty sure the full report can be found on the North Central Texas Council of Government website.
Oh, okay. All right. Very good. And you might want to put that in the question and answer panel then too.
Okay.
And then another question I have here from Catherine is, apologies I missed it, but is the Able Sump model a standalone product dealing with the sump only, or is it part of a larger Trinity River connectivity model?
It's just a model of the Able Sump system consisting of the pump station and its associated 9 ponds and drainage areas. And since Sam is not on our Q&A session, I would highly encourage, if you have any follow-up questions about the Dallas Water Gardens project, his email is available on the website and in the presentation, and he'd be happy to follow up and answer any questions.
And then perhaps the last question is the question about CRS points. Do you know if the community was able to successfully get CRS points for both floodplain management planning and the watershed management planning and the water quality issues?
I assume that, I don't know if that question is related to the Dallas Water Gardens project or in general about CRS. I mean, I know that CRS does provide credit for stormwater management. There are credits for water quality projects, being adopted, like under the MPDS program. I would have to follow up with a colleague on that one if this is related to the Dallas Water Gardens.
Okay, and that would, I think, be useful. So, but in the working out the project, you really weren't looking at the CRS scenarios to decide if there was something that would be done that could help improve the CRS credits.
Yeah, as far as I know, I mean, the reason we included the Dallas Water Gardens project along with our presentation is when this meeting was supposed to be in person, Sam thought it'd be really cool to do, to discuss a project that was local and had an interest to people there. So that is one reason why we gave that project as an example of a green infrastructure type project that could be used in the planning type of process that Caitlin and I discussed.
All right, very good. Chuck, I think we'll move on to the next presentation, and I want to thank Dacia and the crowd from Tetra Tech for the first presentation. Thank you very much. And thank the attendees for inserting the questions into the chat box, and I will encourage you to continue to do that. And as I mentioned to Dacia, she will go in the chat box and actually respond to those. People are going to pull this up later on. We'll be able to look at not only the questions, but her responses to the questions. Appreciate that very much. So with that, I'd like to introduce Stefano Rignanese. I'm assuming I'm pronouncing that right, from Maccaferri, Inc. And the topic of that talk is erosion control applications across the United States, some case studies. So with that, Chuck, I would ask you to cue up the presentation.
And welcome to the erosion control application across the United States case studies presentation for the ASFPM annual conference. I'm your host, Stefano Rignanese. I'm the technical marketing manager for North America for Maccaferri Inc. I really thank you for joining me today. Today we're going to talk about some erosion control application across the United States. But before doing that, we need to start introducing the concept of erosion, which is the definition of the erosion process. First of all, the erosion is a form of soil degradation. So it happens whenever you have a removal of a topsoil of soil due to natural forces such as water or wind, or also can happen through human activities. It starts with the soil detachment. The second step is the movement of the soil due to the natural forces. And at the end, you have the deposition of the material. So you normally have three main steps: the soil detachment, the start of the erosion process, the movement, and the deposition. Normally, the deposition is far from the detachment area. But let's start introducing the type of erosion by water. It depends. The very first step is the so-called splash effect, when you have a direct movement of soil due to the impact, for example, due to the rain, of a water droplet. After you have the second step is that you start to have a uniform removal of the soil, and you start seeing very thin layer on top of the soil. After that, you have the rill and gully area, where you have the creation of a small channels, less than 1 foot, that has carved out on a slope by a running water. And at the end of the day, you have the large channel, more than 1 foot, carved out, but always due to the running water. What about wind? You also have the type of erosion by wind. By wind, you have three main type of erosion, such as the soil creep, when you have a rolling of larger soil particles across the surface, and you have some also bouncing. Also, you have the suspension, such as you have the very most fine particles that are into the atmosphere over long distances due to the strong wind. For example, in Italy, you can find desert particles or soil particles from the desert in the Sahara region, for example. So can run very long distances. And the end, also, last but not the least, the saltation type of erosion, because you have a movement of soil particles where they have sharp bounces along the surface, and you have the displacement additional particles with each impact. But not only water and wind, we said that some other triggering factors can help the natural process of the erosion, such as climatic factor like rainfall. We need to check the amount, the intensity, and the frequency. If we check, for example, the US, when we check the information created USGR JCRP, you can find that in most of the US region, if you check the total annual precipitation and we check the heaviest 1% of the events, in many areas, the indicator shows that increase in the relative amount of rain that falls as heavy rain. So the quantity of heavy rain is increasing, only in the West and Pacific area is decreasing. But most of the country now receive more rain as a heavy rain that did in the past. But not only that, the temperature can affect the erosion process, because the temperature can affect the organic matter present in the soil. And if we check the heat wave frequency, we can see that we have a frequency that is higher and the heat wave season length is always higher. So basically you have that the heat wave indicator shows that the heat wave season has grown longer and how the frequency of heat waves has also increased. So basically the organic matter is affected by this change in the climate, but also the vegetation. The vegetation is very important, is paramount for the protection of the soil. But if we can check, for example, a study made by the Utah University, we can see the difference when we have a good vegetation cover that leads us to only 2% of runoff and eroded soil of 2 pounds per year of eroded soil. While if we have poor vegetation cover, we can have up to 73% of runoff and a loss of eroded soil of 2,718 pounds per year. So it's, as you can see, a game changer if we can have a vegetation cover or if we don't have it. Going forward, we also have some human activities can affect the erosion process. For example, such as deforestation. Deforestation, for example, if we cut the vegetation and the trees that are already in place on top of a slope, what happens is that all the nutrients and minerals are removed from the soils, and also the protection of that particular soil is removed. So that soil that was covered by vegetation now is exposed directly to rain, wind, and all the aspects that we covered before. So basically, if you can check, also the deforestation can affect the erosion process. But what about construction? Construction clearly, when we construct a new residential area, we are changing the environment, we are changing the vegetation, we are altering the gradients and the drainage patterns, we are compacting the soil, and basically what happens is that if we check, for example, in US, the percentage of urban and built-up land area starting from 1980s, 82, up to 2000s, basically we see that the urban areas are increasing. But this, what's the meaning? Because we have higher runoffs and we have always bigger quantities of water because we are increasing the impermeable surfaces on top of the land. But when we saw the definition of erosion, we saw what can affect the erosion process, but also we need to check the erosion control classification. We can check as a source the Federal Highway Manual. You can find it in the design of roadside channels with flexible linings. The Federal Highway divides the erosion control solution into main families, the rigid linings or flexible linings, as you can see, rigid or flexible. The rigid, we can think about soil cement, stone masonry, or, for example, grouted riprap to cover the soil. But what about flexible linings? Also in flexible linings, we can divide in long-term, solution, transitional, or temporary. In the long-term, transitional, temporary, we can always check, the classification, for example, checking the ASFPM or the ICA, the International Erosion Control Association, or also the Erosion Control Technology Council, in order to define or find the definition of this type of systems. For example, today we're going to see examples of a turf-reinforced mat non-degradable used for erosion control application. And in this case, we have some example, just to give you some example of materials that can be used. If we are talking about temporary erosion control applications, we have the so-called erosion control blankets that are degradable. The material can be, for example, coconut fibers, straw fibers, or natural fibers. They are temporary. If we have a transitional solution, non-degradable turf reinforced mat, we also have like a three-dimensional mat that can cover the soil and protect the soil from the erosion action due to the, the water or wind. And also we have a long-term solution such as the high-performance turf reinforced mat, where you have a turf reinforced mat reinforced with a different material. And also you can have such like a wired enclosed riprap or using gabions for erosion control application. But today in the presentation, we are going to focus on the use of geosynthetic for erosion control. And what's the target of these materials? We need to create a physical barrier which absorb water and wind impact on soil. Those solutions are very effective in preventing or limiting the soil loss. And we want to enhance the vegetation growth because we saw how the vegetation influence the erosion control or the amount of eroded soil per year loss. You remember the Utah study that we presented. And also, at the end of the day, what we want to do, we want to increase the shear strength of the soil. But an example, if we talk about the turf reinforced mat, reinforced high-performance turf reinforced mat, we can call about the MacMat R. So the MacMat R is a three-dimensional turf reinforced mat where you have a geomat, that is a three-dimensional erosion control mat, plus the reinforcement, that in this case is a double twist wire mesh solution. This geocomposite can have different tensile strength and different shear strength. But what we want to couple together the double twist wire mesh with the MacMat. Why that? Because we want to create something that can enhance and help the vegetation grow. So this material is designed to work with an in presence of the vegetation. So basically what we want the vegetation grow through the system and the roots of the vegetation can grow through the three-dimensional turf reinforced mat because it has more than 90% of voids. And as you can see, the vegetation can grow easily. But we can also help with different techniques the vegetation grow, such as, for example, the use of local topsoil or imported topsoil with a mix of seeds. Also, you can increase the vegetation covering and vegetation grow a possibility with an hydroseeding on top of the material, as you can see in the left image, left picture. Also, you can have a manually plant live stakes and or potted plants directly during the installation. And very important information, as you can see in the picture in the center, if you have already living plants living in that environment, you don't need to take it out, but you can install the material to fit the vegetation that is already in place. And also, this is very important. We always recommend to check with some bioengineer, local bioengineer, in order to select autochthonous plant, in order to have autochthonous plant growing into the environment. Standard application of these materials you can use to protect from erosion, simple superficial erosion control on slopes. You can have also for heavy erosion control application like hydraulic in the outfall of the culvert, and also, for example, for flexible revetment and soil nailing stabilization for the rockfall application, for example. But let's start talking about some examples because we want to present across the United States some example of erosion control applications. So Texas Fort Worth in 2010, there was a problem with a new development of a new residential neighborhood. As I said before during the presentation, whenever we are building a new residential area, there was an impermeabilization of a very large area. And so there was a formation of significant stormwater runoff during heavy rainfall events. And basically, what the solution, the target of this solution was to create a system to control and try to limit the erosion process. And at the end of the day, the solution selected was the double twist wire mesh reinforcement with the geomat plus the gabions, as you can see. So if you see the application, you have that very close to the culvert, you have the wired enclosed riprap or the mattresses, the gabion, in order to protect the soil. And also on the sides of the banks, you can also install very easily, you can see the turf reinforcement with the double twist wire mesh, where you have basically two materials, two solutions in one. You have the erosion control application plus the steel wire mesh. Sorry about that. And basically, as you can see, we go forward. You can see some pictures of the installation after some time. You have the vegetation growing through the material. And this is what we want. So this is an example where you have the presence of water, so you cover with a long-term solution like such as gabions or mattresses, and after you use on the slopes the magma tar. What about another example? This is in Canada, Montreal. We had a new area that was excavated, and basically they have a problem with erosion. The ideal in this case, because there was a very steep slope, the solution was a soil nailing application using also erosion control application in the slope. Basically what you see, they used the so-called magma tar, and at the end of the installation, the vegetation already started growing through the system. But we always recommend to cover with topsoil, as you can see, the slope, because at the end of the day, what we want, we don't want to see the material exposed. We want to see the vegetation. And as you can see, the final result is a completely well-established vegetation on top of the slope. Basically, another example, moving again to US, New Jersey, northeast region of the US, we have an area that was prone to erosion because there was as you can see, a new development area, and due to heavy rainfall season, there was a big erosion. What was selected as system to cover the soil was the magma tar. In this case, you can also see that it's very easy to install, very quick to install, and basically you can install all in one. You don't need the erosion control and the reinforcement. You can install the material, and as you can see, it's very easy. You have a mechanical connection between the different roles, and at the end of the day, what we want the vegetation growing. So we protect the environment while the vegetation is growing, but the long-term solution is to have the vegetation established there. Another example in Canada, due to another erosion problem at the top of a slope, these cases are very common internationally wise. So in this case, the solution was to fill the global instability that happened. So you fill all that area. You place the erosion control mat with the double twist wire mesh on top, the magma tar, and you fill it and you cover it with topsoil. At the end, as you can see in this case, it's very important to cover with topsoil. While you cover with topsoil, you can also place a mix of seeds inside the topsoil. And what we want at the end of the day, again, is to have the vegetation established, because the vegetation is the one that gives you the shear strength and erosion control, protection long term, and also was added a riprap at the base of the slope. But this is very important to show how the material is completely covered with vegetation. For sure, I need to say that it's very important that before starting with the installation, you have to select the exact or the good mix of soil. Again, it's very important to use autochthonous soil, because if not, autochthonous seed, sorry, because if not, the problem is that you can have some vegetation that can last maybe 1 season, 2 seasons, but they are not, autochthonous, so they cannot live in that environment. So we need to select very good, in a good way, the soil. Another example, moving again into US in Louisiana state, basically there was the Cane River Creole National Park. They had, again, to cover the slopes of the river. And so as you can see in this case, you cover with the magma tar the slopes, and you have the vegetation that it depends also on the type of climate that you can have, and is very quick to establish again. And if you can check the picture at your right, basically you don't see any material below the solution. So what we want the vegetation establishment as soon as possible in order to protect the soil. Last but not the least, we are gonna talk about another project in Texas, and in this case in the Houston area. The date of construction was back in last year, 2019, because after Hurricane Harvey slammed into the coast of Texas in 2017, there was the Buffalo Bayou became a very raging torrent of water and debris. And basically it had significant damages to the bank of the torrent. So the solution in this case was to use the magma tar on the slopes, plus also the use of gabions. In this case, there was the bank stabilization, and as you can see here, a picture during the installation. So on the slope, you can install the magma tar. After, you can create a trench in order to trench and to install the material, anchor the material. And after, this is to show how easy it is to install it. It's very quick and easy installation. And this also is the final result. I want to show you again that the purpose and the aim. So in this case, there was used also some gabions to create terraces. But as you can see, the vegetation establishment was very quick, very good, because again, the vegetation cover is mandatory, is paramount to control, to try to control the erosion. Is very important. And on the other side, just finalizing the presentation, and after we'll leave 5 minutes for question and answer. Basically, we have some special application for dam safety, because nowadays we are seeing that it's very important to protect the dams. You can use also the magma tar against burrowing animals, because they can create tunnels inside the dams and decrease the global instability of the dam. And basically, you can use the magma tar to cover the slopes and you can create a barrier where the burrowing animals cannot enter and cannot damage the dam and cannot create tunnels that can lead to global instability of the dam itself. Here is the final slide of my presentation. Again, thank you very much for attending the ASFPM event. It was great to have the webinar event. It was a great idea. I'm honored to be here. So now we have some minutes for question and answer. Again, here is my contact. Please feel free to contact me if you have any question. Thank you again. And please, let's start with the question. Thank you very much. Bye.
Thank you, Chuck, and thank you, Stefano, for that presentation. We're going to go to the questions now, Stefano. The first one I have for you is from the chat room is there a way that we can design our roadways better so that we can mitigate erosion?
Yes, Larry, thank you for the question. And yeah, the way is to consider in advance when we are designing the roadway which type of soil we have gonna be exposed to the condition like rainfall and wind. And based on that and the type of soil that we have, we should select the best way to protect the slope. For example, we can do just an hydroseeding on top of the slope in order to create the vegetation cover, because the big problem, as we saw during the presentation, is that many times we move the soil and we leave it exposed to conditions such as wind and impact of the rainfall. And then these
background noise.
Yeah, I don't know which.
Yeah, sorry about that, Stefano.
Okay, no problem. But yeah, thank you, Larry. I think I covered
I have one other question here that says, can the MAC-R be used on bog soils or friable mine tailings?
Yes, can be used. Actually, there are many examples or case studies where it was used for such applications. So yes, can be used for that. It's always very important to select the right material for the right application. So whenever they have any additional information, I'm always available to reply and send additional information.
Very good. I did want to mention one thing that the erosion is a key element of managing flood risk, and it's often ignored.
Yes.
For example, communities, when they develop in areas that could pinch the floodway in, they look at whether it increases the flood elevation, but they don't look at velocity, and the velocity is what increases erosion. There is actually a county in North Carolina, Transylvania County, that actually has a no adverse impact approach that says we're going to not only your development must not only it cannot increase flood levels, but it also cannot increase the velocity because we want to avoid erosion. So I think those kind of approaches are very important. Appreciate your getting us into the erosion issues, Stefano. Thank you very much.
I completely agree with you, Larry, because also we need to check not only the velocity of the flow velocity, but also the shear stresses applied on top of the soil.
Yeah.
So it depends on the natural soil that we have on that specific site, and we have limitation, and so we need to check before, in advance, in order to have the protection, the right protection for the soil. And I agree with you, many times the soil erosion is a topic that is like the last to be addressed, and maybe is addressed when you already have a problem. So in my opinion, we should move, or we should change the mentality to check the erosion in advance, before, during the design phase.
All right, thank you very much, Stefano. We're going to move on to our third presentation in this particular session.
No, thank you very much, Larry, and have a great day.
This would be Elise Ibendahl. Elise is with Jacobs. She's going to be talking about mitigating urban flooding in a combined sewer area using a Philadelphia case study. So with that, Chuck, if you will cue up the third presentation, I appreciate it very much.
Hi, my name is Elise Ibendahl with Jacobs. I'm here to share with you the story of mitigating urban flooding in a combined sewer area, which is a Philadelphia case study based on the Germantown neighborhood. We undertook this study with the Philadelphia Water Department. My co-presenter, Eric Hanneman, is unable to be here today, but I would like to let you know that he is the Linear Asset Planning Manager for PWD's Planning and Research Unit, and it was a pleasure to work with him on this project. As an overview of what we will cover in today's presentation, first we will cover the mission statement for the project, and we'll look at the existing conditions in the Germantown neighborhood. We'll further look at the study process, identify the various selected alternatives, and then the path forward for PWD. You might notice that some of the slides refer to CH2M, such as this one does. The project had just started when CH2M became a part of Jacobs, but the CH2M brand was carried throughout this particular project. The Germantown SFR project evaluated selected storm flood risk reduction alternatives and CSO reduction benefits for the Germantown watershed in Northwest Philadelphia. Significant basement and flood surface risks exist throughout the watershed. These risks are related to a combination of factors that include buried historic streams, watershed development, and unique bowl-shaped topography. At the start of the project team, including Jacobs and the city, co-authored this mission statement to communicate the overall mission of the Germantown Storm Flood Relief Study. The mission of the Philadelphia Water Department and the CH2M team is determine the optimum and sustainable combination of structural and non-structural control measures to mitigate the effects of flooding in the Germantown neighborhood while also reducing combined sewer overflows. The system of improvements must be affordable, supported by the Germantown community, and capable of timely design and construction. So there's a lot there. The project certainly had some lofty goals. It's located in Philadelphia along the former Wingohocking Creek, and you can see now that that creek is heavily urbanized and it's been sewered, as many of our urban systems are. Germantown has a long history of wet weather-related basement backups and surface flooding and has experienced multiple significant events. The 9 square mile sewer shed has over 200 miles of combined sewer mains of various sizes, geometries, and materials. The area has over $8.7 million in estimated annual damages, which includes $1.6 million in estimated vehicular damages. 3 distinct storms since 2004 alone have caused over $25 million in damages. And unfortunately, I hate to tell you, these do include loss of life. Existing modeling was developed into a PC Swim 2D model for this study to accurately reflect the surface flow paths. So what you see here on the screen is the surface flooding as developed by the PC Swim model for the 10-year storm. And I'll tell you more about what those red stars are in a bit. So this shows you some PC Swim results for flooding observed during one of the historic flood events, and it was used for model validation. As you see here, we didn't have great data for validating, which is not unusual whenever you're doing a flood study in an urban area. We were given the number of 6.5 feet observed, and the model gave 9.54 feet. We dug a little deeper, and it turns out those stairs are 3 feet tall. So it's very likely that the 6.5 feet was a reference actually inside that church, 6.5 feet of water with no creek anywhere nearby. So the 9.5 model depth that we have is from the ground. So it seemed like they were comparable, especially depending on, the observed measures that we had elsewhere in the watershed. So it's an impressive problem. This shows you what the 100-year looks like from a couple of different perspectives. The 10-year 24-hour synthetic storm event was used as the design event in this study. So most of the figures that you see will show that 10-year event. 6 additional synthetic recurrence interval storm events, the 1, 2, 5, 25, 50, and 100-year events, were also analyzed consistently to demonstrate the potential flood mitigation over a range of storm intensities and precipitation totals. 5 historic storm events that range in magnitude from about the 5-year to the 100-year were characterized using radar rainfall data, and they were used to evaluate existing conditions and each alternative to provide historic context for the synthetic return intervals and design events. The September 28, 2004 event shown here was roughly comparable to a 100-year 24-hour storm event with 7 inches of rainfall and a peak intensity of 3.6 inches per hour. Were present. Radar rainfall data was available for each historic event and used for storm characterization based on the peak intensity in each modeled subcatchment. The highest subcatchment peak intensity for this storm that caused that classic CSO geyser from a manhole was about 3.7 inches of rain in 7 hours. That corresponds roughly to greater than a 10-year storm event. Overall, we characterize this as about a 5-year magnitude. Overall, the rainfall in each catchment ranged from less than 1-year peak intensity to greater than 10-year. That represents the uneven distribution of the rainfall for this event. That's not unusual for the cloudburst type high-intensity events that typically contribute to urban flooding. So what was our study process? Feasibility analysis began with an alternative identification that included specific investigation of a range of specific stormwater management technologies and reviewing various alternatives previously developed by PWD. An initial feasibility assessment screening and updated the existing hydraulic model to include a 2D surface in PC swim. Alternatives carried forward to the next phase were optimized in the AIM2 process, as shown here, with a damage analysis performed for the top performers, allowing selection of high-performing alternatives for further engineering review. The final phase of the project took a more in-depth look at the final 2 alternatives as part of the Aero report. Flood risk reduction and damage risk reduction benefits were quantified for each alternative. A primary metric used throughout all of the phases of the study to determine performance was comparing the flood depths at 24 key flood-prone intersections. We call these FPIs. They were identified by PWD, and they're shown here, with the depths at these intersections frequently used as an indicator of overall flooding severity. Many FPIs are located at bowl locations in the topography, and overland flow velocities into the bowl can be quite high. The maximum flooding depth counts at these intersections during the 10-year 24-hour design storm event were used during optimization and alternatives analysis as a high-level measure of alternative effectiveness. Alternative development began with the investigation of a range of specific stormwater management technologies, including those with which PWD has previous experience, such as the storage tank they've built at Venice Island and tunneling technologies. General categories of technologies included storage tanks, which you may think typically of as a CSO control measure, but they are used here for dual benefit. Tunnels, conveyance upgrades, green infrastructure, and non-structural alternatives for residual flooding, such as backflow prevention, property acquisition, and other site-specific measures. The feasibility analysis and alternative development began with the investigation of about 20 alternatives selected from those initially identified by PWD. Unfortunately, none of these comprehensively address the challenges on their own. You saw that east branch and the west branch, and one might help like the upstream half of the east branch, and then the west branch is out of luck. So it's really difficult to find the right solution to solve all of these problems together. So when used, these problems really needed to be used in combination with others to be effective, but what's the right combination? This figure shows some of the initial alternatives analyzed and compares them based on the cumulative feet of flooding at key intersections for each return interval. A multi-criteria decision analysis tool was also used to screen benefits and effectiveness of alternatives and to explore the weighting of different criteria and to support the decision-making to move into the next phase. The initial individual alternatives selected from what we just talked about and some additional alternatives, including storage and tunnel configurations, were analyzed in combinations with an optimization engine to evaluate the effectiveness over 1,600 unique alternatives formed from combinations of these technologies. The 2D surface was removed from the PC swim model for this optimization purpose and replaced with simplified surface sections representing the known overland flow paths from the 2D to speed the optimization simulations. The optimization engine provided an extensive hydraulic performance screening of both the alternatives and the types of the technologies themselves. Scoring was based on basement flood risk reduction, surface flood risk reduction, and CSO benefits, and provided a thorough representation of the solution effectiveness. Cost, residual risk, and feasibility were also considered. This figure demonstrates the overall optimization workflow goals. First, 20 or 30 standalone options were selected from the feasibility study and run in all combinations using optimization technology. Hazardous damage methodology was integrated with the optimization routine, allowing damage calculations for 90 of the highest performing optimized solutions. A small subset of the high-performing alternatives were selected using the weighted benefit scores for a constructability analysis and additional feasibility and benefit scoring. Ultimately, 2 high-performing alternatives were selected for final investigation. This figure demonstrates the optimization output for the project, comparing life cycle cost against the weighted benefit score. The blue dots represent projects with the largest percentage of cost belonging to storage technologies, orange with the conveyance technologies, and green with green solutions as the predominant component of the solution. An example of high-performing alternative selection is represented by the red circles. The alternatives along the Pareto frontier represent the highest benefit per life cycle dollar spent. Other performance metrics compared in this manner included the FPIs and CSO reduction parameters. 2 alternatives, storage and tunnel, were selected out of the optimization process for further investigation and refinement. The alternative evaluation and recommended outcome, ARO, report develops high-performing selected alternatives and documents feasibility, constructability challenges, and flood risk reduction benefits for each alternative. It also presents high-level planning recommendations for moving forward. The high-performing select alternatives from the optimization process are the storage tank alternative and the tunnel alternative. The report also investigated high-level options for residual risk associated with the 2 alternatives, including backflow prevention, localized alternatives, and green infrastructure. The storage tank alternative consists of 6 storage tanks configured for optimal flood mitigation and includes 2 sewer upsize projects. Chambers, weirs, and conduits were sized to optimize flood mitigation. An iterative process was used to maximize the flood storage potential and reduce the peak storm event flow in the existing system to a minimum. Each tank was designed to ensure that a significant surface flood reduction impact is yielded by each individual tank location. For reference, the pink shading represents the mitigated flood risk, so the flooding that is no longer there in this alternative that's shown as the 10-year. Yellow indicates flooding that's less than 1/3 feet, so minor. And blue shows the residual flooding that is over 1/3 of a foot deep. This is the tunnel alternative. It includes a 60 million gallon storage tunnel and the associated conveyance improvements. The tunnel design evaluated for this report is based on the design that was prepared originally for PWD for long-term control plan purposes by Mott McDonald in 2018. We've added additional trunk sewer improvements, upsizes, that were identified by PWD based on their known knowledge of the choke points in the system. The Mott McDonald team developed the design to meet PWD's objectives for CSO capture, and the Jacobs team investigated feasibility and effectiveness for flood mitigation. That included adding collector tunnels to deliver flood water to the tunnel from the collection system. The alignment provides for up to 60 million gallons of CSO storage for wet weather events in addition to the flood mitigation. The tunnel alignments are shown in red on this figure, and conveyance improvements are shown in green. So what are our results? Flood risk reduction and damage risk reduction benefits were quantified, of course, for each alternative. This table shows a breakdown of our classic FPI flood depth ranges for existing baseline conditions and with the tunnel and storage alternatives during the 10-year, 24-hour storm event. So you can see, for example, for what we consider to be the high priority flooding, anything over 2 feet deep, originally we had 11 intersections at that metric. The storage tank reduces that to 2, the tunnel reduces it to 1. Had the alternative mitigation measures been in place for the 5 historic storm events, significant reductions in damages would have occurred. For example, the August 2004 event would reduce baseline FPI high-risk surface flooding intersections with a depth of 2 feet or more, from 12 intersections to 3 for the storage alternative and 1 for the tunnel alternative, with basement flooding reduced from approximately 2,800 structures to about 930 for the tunnel alternative. This information allows stakeholders to think about alternative effectiveness in terms of storms that they unfortunately remember all too well. Flood damage risk was analyzed using an approach consistent with FEMA's depth damage curve methodology, HAZIS. In this approach, assessed property market values were used on an individual structure basis and were compared against depth damage curves for structures, depth damage curves for contents, content to structure value ratios, and the modeled flood depth of the structure to estimate damage values for each structure. Damages were calculated in a similar manner for vehicles. An annualized damage value was calculated based on a range of 7 storm events for each alternative, using these individual structural and vehicular damage estimates. Damages for alternatives were estimated with and without implementation of backflow prevention, as you see in the table. For example, let's look at the tunnel alternative. Baseline condition damages, including vehicles, are $8.7 million a year that are reduced to $1.7 million a year by the tunnel alternative. If backflow prevention were the only mitigation measure taken, damages would reduce to $4.8 million a year. Adding the tunnel with backflow prevention would further reduce damages to $1.2 million a year. The city estimates that backflow prevention for all structures estimated to be impacted by existing conditions to be approximately $20.6 million, noting that this does not mitigate any surface flooding risk. While backflow prevention for the residual risk on the tunnel alternative would cost $7.8 million in addition to the cost of the tunnel. This table has a high-level comparison of the effectiveness of each alternative against baseline conditions. As shown, each of the alternatives presented reduced surface flooding at over 90% at the key FPIs. And the tunnel alternative mitigates high-risk surface flooding, that's the flooding of 2 feet or more, at 23 of the 24 key FPI locations. Each alternative carries the potential for CSO volume reduction, with the tunnel at the downstream end capturing significantly more CSO, and each alternative reduces annual flooding damages by over 60%, with an 81% reduction by the tunnel alternative. A Class 4 construction cost estimate was developed by the Jacobs project team for the storage tank alternative. A Class 4 construction cost estimate was developed by PWD and Mott MacDonald for the tunnel alternative. This figure shows the cost estimates for the storage tank and tunnel alternatives. So the storage tank, Class 4, is $585 million, and the ranges are shown there, with the tunnel coming in at $384 million. Although each of the alternatives provides significant benefits to reduce surface flooding, the tunnel alternative was shown to provide the largest reduction in flood-prone intersection and basement flooding. This figure graphically depicts alternative performance as determined in this study as a function of Class 4 cost estimate ranges. Planning level feasibility and constructability analyses were performed for each site in the storage tank alternative, as well as for each diversion and drop shaft structure location in the tunnel alternative. Feasibility and constructability issues were identified for each major component of each alternative. Although the identification and documentation of these issues is intended to support PWD planning and alternative evaluation processes, in some cases, additional information or discussion may be needed to fully evaluate feasibility. This may include site-specific geotechnical data and/or integration with other programs affecting system behaviors. Although the extent of the impacts varies for the construction sites inherent in each alternative, some key issues identified during this assessment included difficult access to the site for construction and/or operation and maintenance, the need to acquire temporary or permanent easements in the right-of-way, the potential for extensive rock excavation, the potential for significant temporary disruption during construction, the potential for prolonged community impacts related to operations and maintenance activities, and the proximity to major transportation sites. So, as of now, PWD is evaluating those two alternatives, and as they look forward, there's certain things that they need to consider as identified in the Aero report. Significant design storm, which is the 10-year, 24-hour design storm event, flood mitigation at key FPIs involves significant feasibility and constructability concerns, as well as other factors. Careful consideration of these factors for each alternative must be compared against the flood mitigation and the CSO reduction benefits presented in this presentation and the report. Key considerations for moving forward include the alternative performance. The PC swim evaluation capabilities for complex hydraulic scenarios is admittedly limited, and therefore computational fluid dynamics modeling will likely be required at each drop shaft and diversion location for future design efforts to gain a more complete understanding of hydraulic conditions. It is also anticipated that real-time control gates for either alternative would allow operational flexibility to maximize alternative performance for CSO reduction or flood mitigation as needed. Hydraulic structure analysis. Drop shafts, diversions that maximize flood diversion volumes, tunnel collectors, and the tunnel itself experience significant peak flows and rather impressive velocities due to the urban nature of the system that require an increased level of hydraulic analysis to fully evaluate performance. Laboratory studies and/or a computational fluid dynamics analysis of these elements really is needed before further design to fully characterize system performance and maximize diversion volume. Implementation. Although tunnel and storage alternatives can be constructed as one large project, storage tanks, they can be built in phases, and that's a key consideration. While it's a potential possibility for the conveyance system upsizes to be constructed separately from the tunnel, care needs to be taken to fully understand any negative downstream impacts from doing so prior to project planning and implementation. Of course, there are always the cost considerations. The storage tank cost estimate is significantly impacted by assumptions related to the geotechnical issues at each site. The Class 4 estimates may vary up to 50% to negative 30% from a detailed cost of a specific alternative, and that's important to remember. That's why we show the cost as ranges in the tables. Operation and maintenance considerations. A tunnel system and a tank system have very different maintenance and operational needs. Storage tanks have high operational and maintenance needs, and they require individual attention after every storm event. That includes inspection, cleaning, regular maintenance, and flushing. Tanks also incorporate multiple pieces of equipment that require regular maintenance. Once constructed, the tunnel system can be maintained as a whole system and requires less maintenance. We've talked before about how we've had limited geotechnical information, so that's a consideration. And there are also some regulatory implications. They haven't been fully evaluated, the regulatory requirements. There could be a new outfall into Coney Creek, or we could be increasing the flow into Tacony Creek. In terms of resiliency, PWD may wish to investigate the performance of the mitigation alternatives under climate projected rainfall scenarios to look at resiliency. And in terms of residual risk mitigation, we've talked before, this doesn't solve everything. So the findings of this study can guide PWD to find more detailed localized studies to inform a complete strategy using green stormwater infrastructure, backflow prevention, localized conveyance designs, and property acquisition for addressing that residual risk throughout the watershed. Thank you for your time, and I look forward to discussing any questions you may have.
Thank you very much, Elise. Let me move to a couple of quick questions. First of all, could you explain what radar rainfall data is?
Yeah, of course, Larry. Radar rainfall data is something that the Philadelphia Water Department, they take advantage of that. They are able to obtain archival radar data and work with the vendor to reconcile that with their local rain gauge network to increase the accuracy. So it's a gridded product that tells you the amount of rainfall that fell and the time series in which it fell for every single little square. So the way we took advantage of that was we were able to intersect those grids for each of the historic storm events with the subcatchments that we used in our SWIM model. And from that, we were able to run a more accurate representation of how the rainfall fell spatially throughout the model. That's something that's becoming more and more important as we get into our urban flooding applications, to be able to look at how the rain fell with respect to time across the watershed.
Yeah, so in that respect, I agree with what you just said. It's very good. In that respect, did your modeling include future conditions of future intense rainfalls, or is it backward looking at existing rainfall data?
Right now, we only looked at existing conditions, consistent with the scope of work, but it is a recommendation in the executive summary of our final report that is something to consider going forward.
The city should look at that to figure out, yes, further planning especially.
Yeah.
And then one last question is, what kind of software was used for the system modeling?
Yeah, that's a great question. Primarily, we started with a one-dimensional EPA swim model that the city had started, and it had an extensive approximation of an overland flow network. We noticed that could use some refinement, and since the time they developed that, PC Swim has a really nice surface tool to represent things in 2D. So we developed a 2D grid within PC Swim. Now, when it came time to run the optimization, we used our in-house optimization tool, which is called SimLink. But the 2D models do take longer to run. So, but the advantage of having done the 2D model for existing conditions is that it showed us where those key overland flow paths were. So we were able to take it back to an approximation of a 1D model that came pretty close for optimization purposes.
Okay.
So that was really powerful. And then we took it back to the full 2D for the final optimization of those 9D alternatives.
Very good. Well, thank you very much, Elise. Good information. That's stuff that communities need to think about more all the time. I want to thank our speakers, by the way, and our audience. I also want to thank our sponsor, Tetra Tech, for this session. I want to encourage all of you to go to the exhibit hall that will be going on right after this ends. And then, of course, the final plenary session starts in a half hour. So please be able to participate in that. Thank you very much. I'm going to turn it back over to Chuck.